Hi, everyone, and welcome to Module 9, Lesson 2. Today, what we're going to look at is a couple more ways to calculate delta H, to calculate enthalpy. There is a ton of ways. We're going to look at some more ways today, and then we're going to look at calorimetry and talk about what calorimetry is and how to use it in order to determine things like energy and specific heat. So we'll start off here. It says the standard enthalpy of formation. So we see delta H with a little degree symbol there. That's not, and that means that we are at the standard state. Okay, so when we see this little degree symbol here, it's not, which means we're at the standard state, which is 1 atmosphere and 25 degrees Celsius. So it's different than STP. Standard state is like room temperature conditions, 1 atmosphere, 25 degrees Celsius. But the standard enthalpy of formation is the energy associated with the formation of 1 mole of a compound from their elements. And it says elements and diatomic molecules have a value of 0. Why? Well, that's because we don't form elements. We use elements to form compounds. So the enthalpy of formation is to determine the energy to form a compound from its elements. A state function is a property that does not rely upon a path, but only the start and end point of the process. Enthalpy is a state function because, excuse me, there's so many different ways that we can go about finding enthalpy. Hess's law is one of those ways, and we can do Hess's law a couple different ways. It says that the overall change of a state function is the same whether the conversion occurs in one step or multiple steps. So one way to determine, another way besides the Q equals MC delta T is to determine the enthalpy of formation of the products. You add all those up and you subtract them from the sum of the enthalpy of formation from the reactants. So remember, this little symbol right here from your math class means sigma, or the sum. So the enthalpy of formation, so the enthalpy is equal to the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation from the reactants. Standard enthalpies are given to you in a table, just like this one here. And it says, using these standard heats of formation, we can calculate the delta H for the reaction that's below right here, of methane reaction with oxygen, give me carbon dioxide, and water. So products minus reactants. So we'll take delta H for the reaction is going to be equal to, now we're doing the products, so CO2, which is negative 393.5, plus 2 of the water vapors, negative 241.8. Those are all of my products, minus my reactants. So the methane, there's one of them, so negative 74.81, plus 2 times 0 for the oxygen. And again, oxygen is 0 because it is a diatomic molecule. That's its standard state. We do not form oxygen. That's just the way it comes. So you put this in your calculator, and I really want you to stop this and put this in your calculator to see if you get the correct answer, because these questions, the longer they are, the more things that they have, the more complicated they can be. So just make sure you stop and are able to get the answer of negative 802.3 kilojoules per mole, which should make sense to us. We know that it's going to be a negative. We know it's exothermic because I'm burning methane. It's going to give off heat. Okay. That's just one more way we can calculate delta H. Another way we can do is by looking at a series of equations and basically manipulating them so that when I add them up, they look like the equation that I want. So for example, this is the equation that I want. Okay, I want to find the enthalpy, the delta H for this. I do not know it. But I can use these 3 equations and manipulate them, rearrange them in some ways in order to make it look like that final equation. So what I can do, I can flip the reactants and the products. And what that would do, that would flip the sign of the delta H. I can multiply by the equation, which would then multiply the delta H. I can divide the equation, which will then divide the delta H. So lots of things I can do. The easiest way to do this is to start by looking at these 3 equations. What do I see that's only in one of these equations? Okay, and let's see, I can see graphite is only in this second equation, if that's the first to second. It's only in the second equation. So then you have to ask yourself two things. Is it on the correct side? So I want it as a reactant in my final answer. It's a reactant here. Great. Don't have to do anything with that. Then I have to ask myself, do I have the correct amount? I have 1 in my final answer. I have 1 in this reaction. So this one, I don't need to do anything. It's just going to stay the same based off of that graphite, okay? Now, the next thing I'm going to look at is the methanol. The methanol is only found in this first equation. It isn't found in the other two equations. And so I'm going to ask myself, is it on the correct side? No, it is not, which means I need to flip this equation. Okay. Do I have the correct number? There's 1 here and 1 here. So I do have the correct number. So what I'm going to do is I'm going to rewrite this now when I add and flip it. And I'm going to rewrite my delta H a positive 726.4. And I'm just going to cross it out because I'm done with it. So now I've messed around with the first two equations. Now let's look at the third equation. Is there anything that I need to get rid of in my equation? Because there's nothing that's just specific to this last equation in this problem here. But do I need to get rid of anything? And if I look at my final answer, water doesn't appear in it. So I need to make sure that I can cancel out the waters. If they are on opposite sides, if one's a reactant, one's a product, they will cancel out. If they're on the same side, they'll add up. So I have 2 waters that I need to get rid of. There are 2 waters as a reactant, so I need 2 waters as a product. Well, I have water as a product here, which is good, but now I need to get rid of it. So I need to multiply everything here by 2, which will give me 2H2 plus O2 gives me 2H2O. And my delta H will now be a negative 571.6. Again, cross this out. So now I've got my 3 equations here. Now what I do is I can add them up. I add up the equations. It should look like my final equation that I wanted. After I cancel things out, then I can add up my delta H's, and it will tell me the enthalpy for this reaction. So let's go through what things will cancel out. The waters will. That was the point. We wanted those to go away. Let's see. Oh, the carbon dioxide will. So I have 1 as a reactant here and 1 as a product here. Those will go away. And then the only thing I have left is oxygen. I've got 3/2 oxygen here. I have an oxygen here and I have an oxygen here. These 3/2 will go away. This one will completely go away, and I'll be left with 1/2 oxygen here. Now let me add up everything that I have left. So I'm going to have the C is the graphite. I'm going to have 2 hydrogens and 1/2 of an oxygen, and that will give me CH3OH. And that's exactly what I needed to find, which is good. So that means my delta H, I'm just going to add them up. So 726.1, no, 0.4, plus negative 393.5, plus negative 571.6. When I do that, my answer is going to be negative 238.7 kilojoules per mole. And that's how Hess's law works. Now, I know it might be a little complicated here. So I really suggest that you go into the homework assignment and do some more of those practice ones. And if you'd like, if you want me to, put in the chat and we'll do one of the practice ones in the homework at the end of class, because it can get a little complicated. But the whole idea is to make sure things cancel out so that your final equation, when you add it up, looks like the one that you wanted. Then all you have to do is add up your different delta H's to give you your overall enthalpy for this reaction, which again is negative 238.7 kilojoules per mole. And that's just another way we can calculate the enthalpy. And then finally, we're going to look at calorimetry. So a calorimeter is a very insulated container used to measure heat changes of a system without much heat loss to the surroundings. It can be used to determine the specific heat of a substance. So real labs, like very expensive labs that have lots of money, will have nice calorimeters, okay? Any kind of calorimeter I've ever used involved two basically coffee cups that are nested inside of each other with some sort of lid. Okay, and we do our best to assume that no heat is lost, but obviously this situation isn't going to be the best. This one's not bad because it has an insulated stopper. If we were in class currently, we would be doing this and we would just have literally a piece of cardboard on top. That's the best we would be able to do. So how do we use a calorimeter? So first we measure the volume and temperature of the water sitting in the calorimeter. Then we measure the mass of the object that we're trying to determine the specific heat for. We then heat up the object and determine the temperature before placing it in the calorimeter. We very carefully and quickly put it into the water and measure the water temperature until it plateaus. And then it's very important for a calorimeter. We assume that heat gained by the water was lost by the object. So we can say that the Q of the water will be equal to the negative Q of whatever that reaction is. Okay, because the whole idea is that we're not losing it. So whatever the object gave off, the water absorbed. Okay, and vice versa. Let's say it's an endothermic reaction. Whatever the reaction absorbed, the water gave off. But we're just considering it so none of the heat is lost. It just goes from one thing to the other. So let's do some different situation problems in order for you to understand what we're looking here. Okay, example number 1. A calorimeter with 100 grams of water is at 26 degrees Celsius when a 32.6 piece of metal at 98.3 degrees Celsius is added. What is the specific heat of the metal if the final water is 47 degrees Celsius? Whenever you do a calorimetry problem, this is super important. You always start with Q of the water because you will always know every piece of information. So we always start the mass of the water times the C of the water times the change in temperature of the water. We always start with that. So doing that for this first problem, I have 100 grams. The specific heat's 4.184. And the temperature change. The final temperature it reaches is 47. It initially was at 26. So remember, change in temperature is always final minus initial. When I solve this, it gives me 86.4 joules. Okay. So if that's what the water absorbed, the metal gave off that much. Okay, whatever the water gave off, the metal, no, whatever the water absorbed, excuse me, the metal gave off. So the number is the same, it's just the sign that is different. So then we can do the Q equals MC delta T for the metal. We know the Q, the mass of the metal, 32.6 grams times C, because that's the thing we're trying to find. Now, the final temperature of the metal is the final temperature of the water because they're in the water, and so they're at the same temperature. So that's going to be 47 minus 98.3 degrees Celsius. So you do that math, and the C of this metal will end up being positive 5.25 joules over grams degrees Celsius. It's important to note, a C cannot be negative. So if you've got a negative specific heat, you have to pay attention to your sign. Most likely you didn't do this, okay? So please do keep that in mind. Let's look at the next example. A calorimeter with 150 kilograms of water is at 22.3 degrees Celsius when a chunk of copper at 102.5 degrees Celsius is added. If the specific heat of the copper is 0.385 joules per gram degree Celsius and the final water temperature was 26.7 degrees Celsius, how big was the chunk of copper? Okay, not a problem. We'll still start with our Q of the water. It needs to be in grams, so that's 150 50,000 grams. Again, 4.184. And then the final temperature of the water was 26.7. The initial temperature, 22.3. And the Q of the water will be equal to, it's going to be a big number, 2761440 joules. That's how much water, that's how much heat the water absorbed. Now, for the metal, we just do the opposite. So the Q of the metal will be negative 2761440 joules, which equals, we're trying to determine how big it was, so the mass times the 0.385 joules grams degrees Celsius. The final temperature of the metal was 26.7. The initial temperature, 102.35. When I do this math, the mass will be 94812 grams, which is 94.8 kilograms. So it's a pretty large piece of metal, but that's also a lot of water. It's 150 liters of water. Okay, so again, the main takeaway, we're using our same equation, Q equals MC delta T. We're always finding the Q of the water first, and then whatever the water did, the thing inside the water does the opposite, and then you just use that Q and determine whatever you need to find at that point. It says this last example isn't a calorimeter problem, but we can still do it. It still uses our Q equals MC delta T equation. Calculate the temperature change of 175 milliliters of water changed by 122.3 kilojoules of heat. Okay, so remember our C is in terms of joules per grams degrees Celsius, so I have to change this into joules. Remember, 1 gram is 1 milliliter, so it's 175 grams times the 4.184 times the change in temperature. So I determine the change in temperature is 167 degrees Celsius. That's it. Okay, so it's important to note, again, always start with Q of the water. Whatever the water was, the thing inside the water does the same amount, just the opposite sign. And then you use the same equation to determine whatever it is that you want to solve for. And you've got plenty of practice problems in the homework assignment if you feel like you need to do some more. And now the last thing that we're going to do for this module, I believe, is going to be bomb calorimeters. So a bomb calorimeter is a super insulated thing where we can make sure that no heat is lost. Because if you look at this, the sample is basically completely surrounded by the water. So whatever happens, it goes right into the water and it should not be lost to the calorimeter or to the surroundings. So we have our equation, Q of the reaction is equal to the Q of the water plus whatever the bomb calorimeter is. And we can actually calculate how much energy is absorbed by the calorimeter by using the specific heat capacity of the calorimeter multiplied by the change in temperature. So for example, a 0.444 grams of C12H22O11 is combusted in a bomb calorimeter containing 748 grams of water that changed from 20 degrees Celsius to 22.06 degrees Celsius. The heat capacity of the calorimeter is 0.420 kilojoules per degree Celsius. Calculate the heat of combustion in kilojoules per mole. So we're going to start off the same way by determining the Q of the water. And the change in temperature is obviously 2.06 degrees Celsius. And the Q of the water, 6450 joules. Now we're going to calculate the Q of the calorimeter. So that's going to be the 0.420 kilojoules per degree Celsius times the 2.06 degrees Celsius, which will give me 0.865 kilojoules. Okay, so I'm just going to turn this joules into kilojoules, 6.45 kilojoules. Now, That's what the bomb did and the water did. So now the Q of the reaction will be equal to the negative of these things added together, 6.45 plus 0.865. Because if the water in the bomb absorbed, that means the reaction gave off. Also, it's a bomb calorimeter. You're literally lighting the thing on fire. The reaction will always be exothermic. And that gives me negative 7.32 kilojoules. But if you look in here, it says in terms of kilojoules per mole. So I need to do something with this. And what I need to do with that is turn it into moles. So my 0.444 grams, turn it into moles. I know that 1 mole is 358.28 grams, which gives me 1.24 times 10 to the negative third moles. Okay. And now to get my final answer, the heat of combustion, it's going to be the energy, the kilojoules, divided by the 1.24 times 10 to the negative third moles, which gives me 5,900 kilojoules per mole. Okay. So the takeaway with the bomb calorimeter, I guess I should put a negative sign here. Because whatever the water will absorb, the reaction will always be negative. And that should make sense too, because it's a bomb. So the reaction will always be negative. You add up the two heats from the water and the bomb calorimeter, and then divide it by the number of moles. That's it. So pretty straightforward there. And that's going to be it for this lesson. There is a lot of practice on calorimetry in the homework assignment. So again, it's not a grade, so feel free to do as much or as little as you need to. And if you have any questions or you want to go over any more problems, please just ask, put it in the chat. We can look at that at the end of class. But I will see you later.